In this video, let's address a very interesting question. Why is the resting membrane potential for neuron minus 70 millivolts? But before we can answer that, let's first figure out why the membrane has a potential at all. This is because the neuron has separation of charges. What we see here is a representation of the neuron. And if you zoom into a segment of the axon, you can see there are a higher number of negative charges inside than outside. This is because the extracellular fluid, or the ECF, is rich in sodium chloride and calcium ions, whereas the intracellular fluid is rich in potassium and many proteins. The proteins carry a lot of negative charges, and this contributes to the greater negative charge inside. Note that there are sodium chloride and calcium ions inside too, and potassium and proteins outside, but in much lesser concentrations. The size of the letters here show the concentration of the ions. Larger size indicates greater concentration. Now these ions cannot cross the membrane because of the lipid nature of the membrane. Lipids are hydrophobic and will repel the ions. This keeps the charges separated and creates the negative membrane potential. Now this does not mean that the ions cannot cross the membrane at all. No, but they need special channels or transporters for them to do so. So now we know why the neuron has a negative membrane potential. But why is it minus 70 millivolts? Or if not exactly minus 70, it is very near minus 70. Why is that? First of all, what does minus 70 millivolts actually mean? Well, it means we're setting the outside as a reference point and calling it 0. Now, if the inside accumulates all negative charges, that creates a potential difference of 70 millivolts, then the membrane potential is minus 70 millivolts. But if it accumulates all positive charges, creating a potential difference of 70 millivolt, then we refer to the membrane potential as being plus 70 millivolts. Okay, let's get back to our question. To answer that, let's imagine a neuron is completely impermeable to ions. That is, the ions cannot flow in or out. This neuron will have a certain electrical potential. This is probably some small quantity like minus 10 or minus 20 millivolt. It cannot be large because the total number of ions in the ECF and ICF must be equal to maintain osmolarity. But we know it will be negative because of all the protein anions that are present inside. Now this only accounts for a slight negative potential. But how does the neuron acquire an electrical potential of minus 70 millivolts? Let's find out. Now see what happens to our model when it becomes permeable to potassium ions and potassium ions alone. This means the cell has protein channels that will selectively allow potassium alone to pass through. The potassium is in high concentration inside, so they would diffuse out along their concentration gradient. But when potassium ions leave, the inside will lose positive charges, or in other words, it will gain negative charges, and the outside will gain positive charges. The negative charges that form inside the neuron will exert an attractive force on the positive ions, making it a little harder for them to leave. And the positive charge outside will repel the ions a little bit more. So now, even though a large number of potassium ions will go out, a few will come back in. But as the inside accumulates more negative charges, the negative membrane potential will increase. If it were minus 10 or minus 20 to begin with, it will slowly fall to minus 30 or minus 40 as the diffusion goes on. After a while, the negative potential inside the neuron will be so large that it will start attracting the positive potassium ions back inside. By now, the concentration gradient also would have decreased, reducing the diffusion force slightly. So now fewer ions will go out and most of it will come back in. And they will reach a point at which the amount of potassium moving in and out will become equal. The concentration gradient driving it outside and the electrical gradient bringing it back in. At this point, the concentration of potassium both inside and outside will not change anymore. And the electrical potential also will not change. Or in other words, the system will be in equilibrium. The electrical potential at this point is known as the equilibrium potential. This means if we know the concentration of potassium inside and outside at this point, we can calculate the equilibrium potential. And since potassium is the only ion moving in and out, once this ion reaches equilibrium, the membrane potential will not change anymore. So the membrane potential of a neuron that is permeable to potassium alone will rest at potassium equilibrium potential. And the equilibrium potential of the system can change only if the concentration of potassium changes. Then once again, the diffusion force will drive the excess potassium outside or inside till the system reaches a new equilibrium. But the concentration of potassium is highly regulated in the real neuron, and it does not change usually. Therefore, we can calculate the equilibrium potential for potassium based on this concentration, and it is found to be about minus 90 millivolts. But the neuron does not have a membrane potential of minus 90. The neuronal membrane potential is minus 70. This indicates potassium is not the only ion moving across the neuronal membrane. Other ions like sodium may also be involved. Now, to know how the sodium ion is involved, let's imagine what happens to a model cell if it were permeable to sodium alone. Sodium is in high concentration outside. So the concentration gradient will drive sodium ions in, and the protein anions will also attract the positive sodium ions. But every time a sodium enters, the inside will become more positive, and the outside will lose a positive charge. And as the diffusion goes on, the membrane potential will increase and become positive. After a while, the membrane potential will start repelling the cations, and it will reach a point when the concentration gradient driving the ions in will be equally counterbalanced by the electrical gradient repelling the ions. This is the equilibrium potential of sodium. Based on the sodium concentration in the ECF and the ICF at this point, we can determine the equilibrium potential, and it is found to be about 60 millivolts, which means a neuron permeable to sodium alone would have a resting potential of 60 millivolts. Now imagine what the equilibrium would be if both these ions were permeant. The potassium ions will pull the membrane potential towards minus 90, and the sodium will pull it towards 60 millivolts. And the resting potential would technically be somewhere in the middle at about minus 15 millivolts. But that is not the resting potential either. The resting potential is minus 70, which is much closer to potassium equilibrium than to sodium, which means potassium is exerting more influence on the resting potential. But how is that possible? How can one ion have greater effect on the membrane potential? Well, simple, because the potassium ions are more permeant. The sodium ions do not have as many ion channels as potassium, and its movement will be more restricted. But potassium will move in and out easily. This will keep the resting potential closer to potassium equilibrium, but the slight movement of sodium will try to pull it up. And after this tug-of-war, which sodium loses, clearly the odds were stacked against it. It will eventually rest at minus 70 millivolts. Although I have simplified this talk to the two most important ions in the neuron, sodium and potassium, other ions like chloride also plays a similar role. But being in lesser concentration and being less permeant, they contribute little. And that is how the neuron acquires a resting membrane potential of minus 70 millivolts.